To Margret, thank you for coming to the Kaput Centre. Margret did a PhD with Dick Lesh and has collaborated with John at which department is it? Electrical engineering here at UMass Dartmouth. So it's great to have him here. As you know, the Kaput Centre, albeit focused on mathematics education, is an interdisciplinary unit, and we encourage speakers from a wide variety of disciplines where there's still a focus on mathematics. And so I'm going to hand it over. And we're fairly informal here, so if you wish to have interaction during your talk, that's fine. Okay, versus sort of present formally and then react. So that's good. Okay, so we have an hour and a quarter at your leisure. And over to you. Great. Projector. That's funny. Let's keep it private. God, who gave me the job?
Okay, so while that's warming up, the talk is essentially about, it's titled, The Understanding of Graphs and Functions in Electrical Engineering. And I've been working, we were discussing earlier, I developed a sort of serendipitous alliance with an electrical engineering faculty member at George Mason, who also works closely with John Buck. And our project is looking at, or my piece of the project is looking at how the students understand the mathematics in the within the electrical engineering content, and my overarching goal, of which this project is a slice, is looking at how we look at mathematical thinking from an engineering perspective rather than a mathematician's perspective, and how engineering students apply math and need to learn math in contrast to how teachers or mathematicians might use math, which is what a lot of math education community looks at. Wow, that's huge. Okay. So the two big questions we're looking at is how do students coordinate and interpret multiple graphical representations? And as you'll see in some of the problems that the electrical engineering students are working with, they have to do a lot of activities where they're looking at a graph in one y and x domain, and then they have to translate that same information into another y and x domain over a different characteristic of the function or the system that they're working with. And so how do they make that translation, and how do they coordinate those interpretations? The second kind of question is how do students understand periodicity, frequency, and amplitude? And the quote under there is from one of the students, "I don't know what all those bumps mean." So they see these functions, these bumps, and they don't have a good way of thinking about what periodicity is. And signals and systems is a lot about periodicity and waves traveling through time and all that sort of thing. So looking at the related literature, in terms of graph sense, one definition that's been put out there is how students interpret, analyze, and develop graphs. And then in terms of graph interpretation, how do experts and novices make sense of graphs in different ways? For periodicity, there's some literature about periodicity, but not a lot, which sort of surprised me because I felt like it was a pretty fundamental mathematical concept, looking at periodic functions and things like that. And so there's not a lot of literature out there about periodicity. The other piece that's related to how students understand the higher order, this level of higher order math, it is some of the debate within math education about procedural and conceptual knowledge. And the two definitions I put up are the classic ones from the Hebert and Lefebvre paper, where procedural knowledge is the use of symbols and knowledge about rules and algorithms, and conceptual knowledge is how ideas are connected in a network in which the relationships of knowledge work together. And math education has often put these in a hierarchical sense, where conceptual knowledge is somehow more valuable than procedural. And I want to poke at that hierarchy a little bit. Fortunately, Starr, in the JRME article in 2005, sort of brought forth this idea that you could have deep and superficial procedural knowledge, and you could have deep and superficial conceptual knowledge. And there were two sort of categorically different kinds of mathematical understanding, but both equally valuable. And students could understand them in different ways. So students could have flexible and deep understanding of procedures, and that was a different kind of knowledge than conceptual. Not necessarily better, worse, or more valuable, but just different. Is one of the things he talks about here.
This is John Starr.
Yeah, John Starr. As sort of a side note, when we discussed this paper in my doctoral class, the teachers I had who were secondary teachers said, oh yeah, you could have lots of flexible procedural knowledge without much conceptual knowledge. And the elementary teachers all said, no, you can't have good flexible procedural knowledge without conceptual knowledge. And I don't know why that, and it was the debate my colleague and I had, and I come from a more secondary perspective, and she comes from an elementary perspective. And she didn't see how you could have good procedural without having good conceptual, but some of the data we're looking at kind of shows that there's some of the students have really good procedural knowledge, but no idea what they're doing.
I think this debate has risen to the surface again because of things like the TIMS and the PISA studies,
Right.
where procedural thinking are procedurally complex tasks, which are multi-step or that I've just written a paper on it. I forget what the terms are, but it's readdressed the question of what is a deep procedural question in terms of levels or sub problems, and
Yeah, so it's sort of come to the surface again. The other thing that comes out here is part of the Kramer and Lesh, but I think other people have put out these 5 categories of representations, looking at graphs, symbols, pictures, real world, and words. And the engineering, a lot of the engineering problems in signals and systems, even though they're talking about hypothetically real signals, they're presented in a very abstract fashion, absent of the context. They'll say, here's a signal, and who knows what it's a signal of. It can be a signal of anything. The other piece is, I think in math education, and go ahead and disagree, but I think there's been a lot of looking at how we move from symbols to graphs and back and forth, but not much within graphs. How do students look at different versions of graphs that represent the same situation?
I don't think we'll argue, but that's kind of our bread and butter here.
What?
Right,
and SimCalc, and SimCalc, and there you're looking at the velocity versus
Right,
acceleration versus time.
Yeah.
I'll show you how this is sort of slightly different.
Some of it, this is also, I wouldn't say so much different perspectives though. Different graphs are the same thing, how two different graphs interact. The graph of the
Yes.
signal and the graph of the system, based on that.
Within a graph.
How those two graphs interact to form a third graph.
Right. Again, like I said about periodicity, I was, again, sort of surprised to find the lack of literature on periodicity. And what Shama talks about is that it's a process involving time dependency and motion. So you have something moving over time. And some of students' knowledge about periodic functions, their sort of basic algebra class knowledge of periodic functions, transfers when they start getting into their work in signals and systems, and some of it goes horribly wrong. So, since I've been talking about signals and systems, and I'll be careful since I've got signals and systems engineers sitting here. It's essentially, it's a discipline, a sub-discipline within electrical engineering, with looking at applications with radio waves, sound waves. I think John studies the noises that whales make and water. There's a lot of mathematical techniques. It's very heavily mathematical. Looking at Fourier analysis, Laplace transforms, lots of sequence and series. I've had to relearn most of that in order to do this project. But there's a lot of heavy mathematical techniques that go into the work that they're doing. So how this project came about was John and Kathleen, my colleague at George Mason, were developing a signals and systems concept inventory. And they were trying to assess students' conceptual understanding of signals and systems processing. So focusing on what were the really big ideas from the discipline, and how to